Okay, moving on to section 2.3, getting information from graphs. So we're going to look at values of functions, looking at the domain and range. We've done that a little bit, so we're just kind of expanding on that. We're going to compare function values, solving equations and inequalities graphically. We've done a little bit of that as well. Increasing and decreasing functions, local max, local min, also fairly easy stuff. So it should be an easy section. So many properties of functions are more easily obtained from a graph than from the rule that describes the function. We will see in this section how the graphs tells us whether the values of the functions are increasing, decreasing, and maximums and minimums of the functions. So first of all, domains and ranges. As we've seen before, the domain is all the possible input values. The range is all the resulting output values. Right? A complete graph of a function contains all the information about the function, because the graph tells us which input values coordinate to which output values. Okay, so we want to analyze the input and output values. Here's an example. Let the function t graphed in figure 1 gives the temperature between noon and 6 p.m. So here is between noon and 6 p.m. So x, the input value, is the time. So here x equals to 0 represents noon. So here, this value right there would represent noon. And then this is 6 p.m. And then we have our temperature, right? So temperature in Fahrenheit, it starts off, looks like 15 at noon, and gets warmer and warmer and warmer. And looks like we hit the highest temperature of looks like about 35 or 34 around 2 p.m. And then temperature begins to come back down, and we get back down close to 15 by the time 6 o'clock rolls around. Okay, so we have a nice little picture to describe the temperature. So let's find some values, some information from this graph. So for example, let's find t of 1, t of 3, and t of 5. So this notation, this is function style notation, right? So this is letting us know that I want the temperature when the input value is 1. So this is x equals to 1, when x equals to 3, and when x equals to 5. So all we have to do is read 1, 3, and 5 from here. So when the input is 1, this traces up to this point right there. So it looks like the answer is going to be about 25. When it is 3, looks like it goes all the way up to there. So that looks like it's going to go up to about 30. And then at 5, it looks like it goes up to there, which is again about 20. Good. So it looks like we have the ordered pair 5, 20. At 5 o'clock, it should be about 20 degrees. At 3 o'clock, we get the ordered pair 3, 30, approximately. So it should be about 30 degrees at 3 o'clock. And at 1 o'clock, we get the ordered pair 1, 25-ish. So we get those results. 25, 30, 20. 25, 30, 20. Good. Very easy, right? Okay, which is larger, t of 2 or t of 4? So t of 2, okay, so here is 2. T of 2 reaches to there. Now remember, it's not exactly up to that level, so it's not exactly 35. It's a little less than that. In fact, let's make it a different color since I don't want to mix it with the other ones. I don't know, let's make it blue. So t of 2 is here, and t of 4 is here. Right, so we wanted to compare t of 2 and t of 4. Right, those were the instructions. T of 2, t of 4. Okay, so people often confuse this. The input value is 2 for this one. The input value is 4. So of course, 4 is bigger than 2. But t of 2 represents the output. It represents this. So this height right here is t of 2, whatever it is. T of 2 is somewhere around there. Whereas t of 4 looks like it's exactly this, so maybe t of 4 is somewhere around there, around 25. So here we could see that t of 2 is higher than t of 4, right? So t of 2 is greater than t of 4. Good. T of 2 is bigger than t of 4. follows that T of 2 is larger than T of 4. Yep, that's what we wanted. Okay, next question. Find the values of x for which T of that value equals to 25. Equals to 25. So we kind of want to reverse engineer this and find the values that work. Let's erase this stuff over here. Okay, so 25 is here. The output is 25. And we want to find all the values of x such that f of t equals 25. So if we kind of go back, we see that there's 1 point there, and then we kind of go backwards and see that the answer would be 1. If we let x equal to 1, we should get an output of 25. And then again, going backwards this way, we run into the other one. And it looks like the other answer is x equals to 4. So in solving this statement, oops, right, x equals to 1 and x equals to 4 are the two potential solutions to this. 1 and 4, so the temperature at 1 o'clock is about 25, the temperature at 4 o'clock is about 25. Man, can you imagine living in a place where the warmest part of the day is 34 degrees? Not fun. Anyway, find the values of x for which t of x is greater than or equal to 25. Very similar to this previous question. Except here we want to find all the values where t of x is equal to or greater than 25. And so that's going to be this section of the t-axis. Come on. Starting from here, I want to figure out all the input values that result in a value higher than 25. I want f of t to be greater than, so greater than or equal to, yeah, greater than or equal to 25. So I want to find all of these values, right? So it describes this part of the curvature, like that, right? All of these output values are bigger than 25, and then if I trace that down to the shadow, we see that all of these values, let's put a different color on there, how about orange? We see that all of these values between here, all of these inputs, including 1 all the way up to 4, all of these values are the values such that the result, the output temperature, is above 25. Right, so all the values between 1 and 4 result in a function that is equal to or higher than 25. So between 1 and 4, the temperature will be above 25. And then last one, find the net change in temperature from 1 to 3 p.m. 1 to 3 p.m., the net change in temperature. Okay, so let's find them between 1 and net change in temperature between 1 and 3 p.m. So between 1 and 3 p.m. Come on, there it is. Okay, so here is 1, and then that changes to there, and then 1 and 3 p.m. So this changes from there to there. So if we think of this little triangle that can be formed underneath this curvature, and maybe orange isn't the best color, we can look at this little triangle here, and we could see that this represents the change in the output temperature, whereas this represents the change in the time. So the distance from here to here is the change in the x, but the net change in the temperature is described by this, which is the f of, the t of 1 value, which is this value there, and then this one, which is the t of 3 value, which is, looks like it's about there. So we can see from the graph there's a net change of about 10 degrees, right? This goes from about 20 degrees up to 30 degrees. So the net change is going to be 10 degrees. Net change is 10 degrees Fahrenheit. Let's see, and then what did they put on here? Oh, wait a minute. See, look at this. What did I do wrong here? 25 and 20, f of 1. See, look at that. I read this wrong. Well, this was just way off. This is definitely a good point. T of 1 is not 20. I don't know where I got 20 from. 20 is way down here. T of 1 is this. This is 25. My net change is 5. It's not 10. Right? So this guy traces over here and gives me a 25. And that's T of 1. T of 1 goes to 25. So the net change here is not 10. I made a mistake. It's 5. So in general, whenever we're given a curvature, some sort of graph, described here in the red, this is the graph, then as we kind of see, think of this as the shadow. If we see the shadow of this curvature along the ground here, around the x-axis, that describes the domain. So this is all possible inputs of this defined curvature here. So that would be the domain. And then this one gets a little more confusing for people. It's all possible outputs. So if we kind of slam it across this way, or the shadow across the y-axis, right? If we have a giant light source over here going this way, we see the range values. That often gets confused with this. Let me put some numbers on here. Just to put some numbers on here, let's say that this is the number 1, 2, and this is the number, I don't know, 7, 8. So the domain is going to go from 1 to 7, right? So the domain can be described as 1, 7 with brackets. And the range, so this is where people get confused. So here is the range 2, and they think it's from 2 to 8. But that's not it, because the 8 is this number right here. But that's not the highest possible value. 8 only maps to like around there, right? I want this point. This is the one that's going to tell me the maximum value on the range. So if this was labeled as, say, I don't know, 6, 10, then the range would go all the way up to 10, right? So this would be the range. The range would be 2, 10, inclusive. Right? Whereas this is the domain. So my point was just that it's not just about the last point and the first point and the last point. That's not always the way to find the domain and the range. You have to be careful to make sure that you are inclusive of all possible inputs, all possible outputs. Again, if you're just given a graph, a picture, then you just have to look at the picture and judge from the picture what the domain and range are. And again, you can't be super precise when just the picture is given. But when we have an equation, it's a little bit more complicated then, because we have to take our equation and figure it out from there, figure out what the domain is and figure out what the range is. And particularly the range can get a little confusing, a little difficult to find. Okay, for example, use a graphing calculator to draw this graph. And then find the domain and find the range of this graph. Okay, so let's first of all use Desmos, and then I'll look at our graphing calculator. So going to Desmos, x equals to, once again, root here, sine root of 4 minus x squared. 4 minus x squared. Okay, so it says to graph it, so this is that's what we're supposed to do, find technology and graph it. And Desmos does a great job, so here it is, that's what it looks like. And so from the graph, we can tell what the domain and range are going to be. So the domain is going to be all possible inputs, so that's going to be all values trapped between -2 and +2. Right? Any one of these values can be plugged into this equation to give us a possible answer. Now, why aren't any of these values in there? Think about what happens when we try and plug in x equals to 3. If we plug in an x equals to 3, we're going to get 4 minus 9. That's -5. The square root of -5 is an imaginary number. So there is no real number solution when x equals to 3. Good. So the only real number solutions come when the x value is between -2 and 2 inclusive. What are the possible output values? Well, it's always positive because we only have the positive root here. So the output values can only be positive answers. And then the smallest value it could be is 0, because if we let x equal to 2, then we get 4 minus 4, which is 0. Square root of 0 is 0. So the smallest value this could be is 0. And what's the biggest value this could be? Well, we're always subtracting a positive number, so the biggest value inside the radical occurs when x squared is as small as it can be, and the smallest it could possibly be is 0. So 4 minus 0 squared is going to be 4, and the square root of 4 is 2. So the largest possible value that this can take on is a 2. So from the graph, remember this is at this point we're just trying to solve this by graphing. So we graph it, we see the picture. So from the picture I can tell the domain is between -2 and 2, and the range is going to be from 0 up to 2. This is kind of like the top half of a circle, right? And this goes from -2 to +2 to +2, and so the domain is going to be all of these values over here. That's the domain. And then the range is going to be all the possible output values that we get, which is going to be all of these values here. So the range is going to go from 0 through +2 inclusive, and the domain is going to go from -2 to +2 inclusive. So let's look at how to graph this on a calculator. And the short answer, okay, so let's see if it'll work, because I have a lot of programs working and the computer is not happy. So let's see. This is the screen that normally sits right above your calculator, right? That's what this is. They just made it a little larger. So what we want to do, whenever you get your calculator, the first thing you want to do is go over to where it says mode and check the status of your calculator. So it's in normal mode, it's in float. If we type in an angle, it's going to be in radians. It's in function setting, that's what we want right now. Later we'll look at parametric polar functions. Dots are thick, sequential, real numbers, full. Okay, everything looks pretty good here. If something is not like this on your own calculator, you can use your arrows here, go left and right, down, up and left, right. And if you want to select something, then you hit enter. So if I wanted to change it to degrees, for example, I can select degrees, hit enter, and then now it's in degree mode. Good. Put it back in radians, enter, we're good. Okay, so now when you want to get out, hit quit. So the little quit button is right above where it says mode, but it's written down. So we have to hit second, and then mode, and that qualifies as the quit, right? In this is really old technology from like the 80s maybe, these calculators. So a button can do different things based on the writing. So there's like the actual button has writing on it, but there's a little writing above in different colors. So if you want that other value, you have to hit the second or the alpha buttons first to give you that result. So if I wanted to type in 7, for example, I could just hit 7. But if I wanted the green O, then I hit green, and then I hit O. And, well, that looks like a 0. So let's do P. If I wanted P, I would have to hit the green first, and then the 8, and then that writes down the P. If I want V, then I would hit the second, and then that gives me a V, and I type that in. Okay, so keep that in mind. All right, so to graph that equation, we're going to go to y equals. That gives you this kind of a thing. And we want to type in a giant root. Now, a giant root on your calculator is pretty ugly to do. But okay, so it's right here, a giant square root. So we're going to hit second and then root. That puts the whole thing in a giant square root. And it was 4 minus x to the second power. So there's an easy button for x squared, which is this one. And this is the value of x, right? The variable x is going to be right here. And then we want to have that squared. So 4 minus x squared. Good. Hopefully that works. Now, an alternative way of doing it is to use those power symbols, the little caret symbols. So instead of doing the square root of, I can say that this is equal to, and let's put it in parentheses, open parentheses, and then 4 minus x squared, close parentheses, and then to the power of, that's what this little caret symbol does, to the power of. Now the newer calculators do this kind of thing where they bring you up to the little exponent. If you have an older calculator, you see the little caret symbol appear, and you have to know that that means that you're in the exponent. So now we can raise it to the power of 1/2. Good, so this is the same as that. No? Okay, so next we're going to go over to our window. well, okay, so let me erase this. I don't want them both. Just pick one of them. So to graph that, okay, so now I'm going to go over to my window, and I got to choose a good window. Let's pick, I already know by default, I kind of already know what I'm graphing. I'm going to graph this. If you don't know what you're graphing, then the window of -10 to 10 is good enough, and then just kind of play around with it, or -20 to 20, right? So what we're choosing is the x minimum. So the x minimum is going to be this value over here. How far to the left do you want your window to be looking? And x max is going to be over here, the maximum value. And then y min, y max, same thing. Minimum y value, maximum y value. We'll play around with those for change them to see what would happen if we change those. When you're done typing in the values you want there, you hit graph, and you'll see it there. So because I put -10, +10 for the x min, x max, and y min, y max, that means that this is -10 here, and way over here is +10 for the x min, x max, y min, y max. As you can see, it's a bit of an overkill. The picture is way in the center here, so what we could do is go back to our window and bring this in a little bit. How about if I make this -3 to +3, and I can make this, I don't know, how about -4 to +4? Graph. And so you see I have a slightly better picture now. So this goes out to -3 and +3, x min, x max, y min, y max. In fact, I could tell I don't even really need anything down here. The actual graph does not go into quadrants 3 and 4. So if I wanted to, I can go back to my window and set my y minimum down to 0. And then the graph would look like this. Oh, even better. Looks a little more like that one. Good. So you can just kind of play around with the window settings to make sure you catch your whole image. Be careful though, because if you do something like, let's make this go from -10 to positive, let's say it's a -5. If I choose a window like that and I graph it, I'm not going to see anything. My picture's not there because I focused my window so far to the left. It's in just a small little section of quadrant 2 that my picture is not in the image. Right? It's somewhere over here. So be careful to choose a good window for your graph. Like I said, by default, if you don't really know what you're doing, you might want to pick a standard setting like -20 to +20 and see if that kind of gives you an idea of where the graph is. Right? And of course, keeping in mind that these calculators are really old, the screen doesn't really have that many pixels, so you get kind of a warped sense of the picture often. So keep that in mind. Okay, so back to this guy. Okay, so we got the domain, we got the range, we could graph it, we feel pretty good about it. Here's another nice little image of the whole thing. So we have the range, we have the domain, and we get all that from its graph. Good. Okay, comparing function values, solving equations with inequalities graphically. Okay, we can compare the values of two functions f and g visually by drawing the graphs. That's another great way to use graphs. You can figure out when they equal each other, which is where they cross, where they intersect. And then from those, we can easily tell when one graph is larger than the other from the graphs of the two functions. Good. So, for example, if we have a g function and we have an f function, we can easily tell from the graph when they cross there and they cross there. That means at x equals to a, both f of a and f of g, g of a and f of g, and f of a equal each other. Write that down. Saying that at this point right here, this is a point where f of a equals g of a. Come on, at that point right there, right? And at this point right here, this is a point where the output of f, which is at b, f of b, equals to g of b, right? So we can easily tell when both of these equations are going to be equal to each other right when they cross. And we can also tell the sections of the domain where the g function is larger than the f function, or where the f function is larger than the g function. Good. So we can tell that in this little segment of the domain, the g of x function is going to be larger than the f of x function. So this part right here is true. So if we were trying to solve this find x such that f of x is less than g of x, we know that if we graph it, we can visually tell when that's true and find the domain that solves that. Okay, so for example, solve the given equation or inequality graphically. Okay, so don't solve it algebraically, solve it graphically. So we have 2 of x plus 3 equals 5x plus 6. Okay, so the first thing we want to do is define the left-hand side of this equation by some function f of x, and define this side of the equation by some function 5x plus 6. Next, what we want to do is graph them both and figure out where they cross. So again, we can use technology. Let's use Desmos again. Desmos, graphing calculator. Okay, so we're going to define f of x to be the left-hand side, which is equal to 2x to the second power plus 3. Right, that's this part here. And then we're going to define g of x to be the right-hand side, g of x to be equal to 5x plus 6. Okay, so here is the graph. And from the graph, we can easily tell where they cross each other. So here's one intersection point, there's another intersection point. So Desmos makes it extra easy. You just have to get kind of close to it and click, and it'll show you where they intersect. With the calculator, it gets a little trickier. We'll cover that in a second. But we can easily tell that these are the 2 points where they will equal each other. So when when the input equals to negative 0.5, both functions will have the same output of 3.5. And when x equals to 3, both functions have the same output of 21. So those are the 2 solutions to this equation. So now that I have the really nice graph over there, then I can do like a really, whoa, not that ugly, like a really rough sketch of what this thing looks like. And do I have a, well, okay, never mind. So from the Desmos, I could tell that this was the general graph. And we could tell that these ordered pairs right there were 3, 21. And the other one was this one, negative half and 3.5. Good. So we can tell that those are the 2 answers to part A. F of x and g of x are equal to each other whenever x equals to negative 0.5. Negative 0.5 is x there. And x equals to 3 is the other answer. No? We'll cover how to find that intersection in the calculator real quick in a second. Okay, next, when is the 2x squared plus 3 less than 5x plus 6? Okay, so we said the way I defined it, this one is f of x. When is f of x, which is the parabola looking thing, less than g of x? That's what we're looking for. When is f of x less than or equal to g of x? And again, from our picture, when is the parabola smaller than the line? So we could tell that that's this little zone right in here. Okay, so I can tell that in this zone, in between these, for this domain right here, in this little section right in here, oops, then in this little section in green, it's true that the f of x function is less than the g of x function. So for part B, the answer is going to be this set between negative 0.5 and positive 3, inclusive of the endpoints because it wanted that. And then, of course, the opposite, when is the f of x function greater than the g of x function? Well, that would be for domain values over here on the left-hand side or over here on the right-hand side. Okay, so for part C, we get the opposite. For any one of these values, the f of x function, right? So like if this thing is a value of x, if we choose x to be, I don't know, what is this, 1, 2, 3, negative 3.5, for example, then this would lead to some value there of the f and some value here for the g, and then the f would be larger than the g. Good. So this and this, which is described this way, is the sections of the domain for which the f of x is greater than the g of x. Sort of, kind of, maybe. Okay, so then let's cover how to use our calculator to do that. Okay, not as easy. So we want to type in 2x plus 3, 2x squared plus 3, and then 5x plus 5 on your emulator. So let's go back over here. So we want to go back to y equals. Let's get rid of that one, the old equation. And we're going to type in 2, x is this button here, the power of caret squared, so that's 2x squared. Make sure you put the arrow to get away from the exponent, and then plus 3. So that's one equation. And then the other equation was 5x plus 6. There's the other equation. Let's pick a good window. By default, let's just try -10 to 10. Nice square window, and assess it from there. -10 to 10. And see what it looks like. Graph that. So there's the parabola, there's the line, and I can see, oh, look at that, it's out of the window. So I'm going to go back and readjust my window. I don't need to go all the way to -10. Looks like -1, 2, 3. Looks like -3 captures everything I need on this side. And then on this side, it looks like, well, it's kind of hard to tell exactly where it's going to be, but maybe around this far. It's really the positive y maximum value that I want to increase. So let's go to this. -3 we said was good enough for the x. Let's go to a y maximum value of, say, 40. See how that covers it. There we go. That looks better. Okay, so I need to figure out when these two things cross, where they intersect. Using our calculator. On Desmos, you just click it and it just gives it to you, but we don't have that clicking ability on our calculators. So we're going to use this button that says trace on here. Above it, it says calculate. That's what we want to do. Trace is the easier way of solving this question, and some teachers might be okay with that, but it's also very imprecise. So it's just a couple extra buttons and then you get a more specific answer. Use this little button that says calculate. So hit second and then calculate. And what we want to do is this, the intersection. So go down, use your arrows, hit enter, and then follow the instructions. First curve, question mark. Okay, so look, here's the first equation. It was a parabola in blue. And then if you hit up, then here's the second equation, and it's this one. And you can just keep going up and down, right? Up and down, and it'll just go back and forth between them. There's only two, so it seems like kind of a silly question. But keep in mind that I might have a case where there are a lot of graphs. One graph is a parabola, another graph is a circle, another graph is a line, somehow a absolute value in there. There could be lots of graphs in there. So when you ask the calculator where do they cross, it wants to know which curvatures. So all you have to do is hit enter, and then it asks you for the second curvature. It automatically jumps anyway to the other one, so you can hit enter again. So when you only have two equations that you're dealing with, you just have to hit enter twice. It's really when you have 3 or more functions that you have to care about making sure that you're choosing the correct ones. Okay, next, the third question now is for you to guess. And so you just use your arrows to go left and right. See how I can go left and right, travel on the curvature. Right now I'm traveling on the straight line because I have this equation there. So I'm traveling left and right on it. On the other hand, if I go up by 1, didn't want me to do that? I thought it did. Never mind. I thought it let you jump to the other equation. For some reason, it doesn't seem to want to do that. Anyway, it's asking you to guess. So travel along that curvature until you get to the one that you want to approximate. Notice that there are obviously two answers. So if I just hit this right now, the calculator won't know which intersection you want. So you just have to get fairly close to it. You don't have to be super precise. It's somewhere around there. Just close enough so that the calculator knows that you want this intersection as opposed to this intersection. Okay, so hit enter. It'll calculate it and then give you the exact answer, 3, 21. So all that work was to mimic what Desmos does right here when you click this, and then just gives you 3, 21. Okay, to find the other one, to find this one over here, you have to repeat the whole process again. So now if I want to figure out when does it cross over here, we're going to have to hit second, calculate, the fifth option down. So you can either use your arrows down, hit 5, enter, or you can just hit the number 5, and then follow the instructions. Remember, when there's only 2 curves, you just have to hit enter twice. Pick the first curve, pick the second curve, and then get to the part where it says guess. And now we want to get away from that guess and come over here and try and guess this one. Hit enter, and now it gives you the other solution, negative 0.5, comma 3.5. Okay, so once you graph them, once you find the intersections, then you are able to solve these types of questions. When are 2 functions equal to each other? When is one function greater than another function? And that could be really useful. Okay, moving on to increasing and decreasing functions. Spotting when a function is increasing and decreasing is very easy from a graph. And initially, that's all we're going to do. So a function is going to be given, like this one, and you just have to identify the segments of the domain for when the function is increasing, and the sections of the domain for when the function is decreasing, and so on and so forth. Doing it from a picture just involves looking at it and judging it, and hopefully that's really, really easy. What we're doing is we're building toward being able to do the same thing when we're given an equation. Right? So you can picture this as an ugly polynomial equation, right? X to the 5th power minus 4x cubed plus 7x, something like that. And then looking at just the equation, how can we tell when the function is increasing, when it's decreasing, right? So some of the key characteristics of it. Well, if you're just given an equation, one thing you could do is, of course, use technology to graph it and then judge it from there. But if you don't have the technology, how can we do it? Well, that gets complicated, right? That's what we're building toward doing. But for now, all we have to do is look at the graphs. So this section is still very easy. And I think it's pretty intuitive of when the function is increasing. Here it is. It's going up. You can picture a little person walking on it from left to right, the way we read. And if that little stick person, here's my little stick person. Wow, it's a terrible stick person. There. If that little stick person is going up from left to right, the way we read, if it's going up, it's increasing, kind of like slope, same as slope. And then if that little person is going downhill, from left to right, the way we read, if he's going downhill, then that's decreasing. Good? Questions, 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 questions? Okay, so from a picture, we can easily tell when he's going up, he's increasing, decreasing, right? And so we can tell the sections of the domain where the function is increasing. F of x is increasing between a and b, right? So this is for x between a and b. The function is increasing. For x between b and c, the function is decreasing. And for x between c and d, the function is increasing, right? So we can easily tell from the picture. Again, we're just building toward being able to do it with equations down the road. And then a more precise mathematical description of what it means to increase and decrease is this guy. Don't let this scare you too much. It's just kind of building on our understanding of mathematical expressions, but it's really a very simple explanation that, again, you can just kind of visually see it, right? This is increasing, and this is decreasing, right? Again, a little stick person walking from left to right would be going uphill here, and a little person walking from left to right, the way we read, from left to right, or most of us, will be going downhill. So this is decreasing. So symbolically, what we can say is that this function is increasing if it's true that f of 1 is less than f of x of 1 is less than f of x of 2 whenever x of 1 is less than x of 2, right? Which is exactly what we see here. Whenever it's true that this one is smaller than this one, right? The smaller one, if we evaluate it, leads to an f of x sub 1 that goes right around there. Let me erase that stick person who's in my way. Okay, so f of x sub 1 leads there, and then f of x sub 2 leads there. Pretend those are straight lines. X sub 2. And you see how f of x sub 2 is the larger value. F of x sub 2 is larger than f of x sub 1. whenever it's true that f of x sub 2 is larger than f of x sub 1. When the bigger value in the domain leads to the bigger value in the range, then we have a case where it's increasing. And then the opposite is true. When the bigger value in the domain leads to a smaller value in the range, right? So here is what f of x sub 2 leads to, and here is f of x sub 1, f of x sub 1. So in this case, the f of x sub 2, this one leads to, it's bigger than this one. F of x sub 2 is bigger than f of x sub 1, but the output, let me say that again. X sub 2 is bigger than x sub 1, but the outputs are the other way around. The f of x sub 2 is smaller than that one. So whenever that's true, we have a case where the function is decreasing, right? F of x sub 1 is bigger than f of x sub 2 whenever x sub 1 is less than x sub 2, right, on that interval. Okay, so don't worry too much about this definition right now. This is not a difficult section. We're just trying to find a math way of describing increasing and decreasing for graphs, but you could just look at them and be able to judge when that is. Good. And then just spend some time looking at this. I think eventually it'll click in. If we wanted to sketch a more complicated graph like this one using technology again, we can type in this polynomial, and then from the polynomial we can find from the graph of the polynomial we can find the domain and the range. The domain is going to be really easy, right? Because it's a polynomial. The domain of all polynomials is all real numbers. There is never any value I can input into this polynomial that would result in either a undefined, that would result in undefined from either dividing by 0 or taking the even root of a negative number. The more complicated thing is to figure out the range. Right? What is the maximum output of this? What's the minimum value of this thing? And so it'll be easier to find the range by graphing it. So find the intersection on which f is, or find the intervals on which f is increasing, on which f is decreasing. Okay, so let's do it with Desmos first, and then so this is going to be 12x to the power of 2 plus 4x to the power of 3 minus 3x. And let's get rid of this guy. 3x to the 4th power. Okay, so I typed in the correct answer, 12x squared plus 4x to the 3rd power minus 3x to the 4th power. Okay, so this is what the graph looks like. And it keeps going on that way forever. So I know the domain is all real numbers. But the range, I could tell that the biggest value this could ever be is described by that value right there. Right? So the range is everything below that. Everything below 32 is the range, where the domain is all real numbers. It might look better if I zoom in. Right, so now I can do a rough little sketch here. This guy. And I know that this is going to have, let's make it this way. It did like a little thing and came up here, whoa, and then came up there, and then came back down here. Ugly little sketch, but if we find some of the key values, it's good enough to be able to describe what this graph looks like, right? So if they wanted a really nice sketch of this, it would be nice if I found this point, that point, that point, that point up there, that point down there, and then indicated that it went down toward negative infinity from there. They didn't ask for an incredibly detailed graph, so I think this is good enough for now. We just have to find a few of these key points. And again, Desmos does a fantastic job of all of that. So I can identify this point, and that point, and this point, and that point, and that point, and find all the key features I want of this graph using technology. If I didn't have technology, then this would be a whole lot of work, and that's what we're building toward. Finding all the places where it crosses the x-axis. Those are all the x-intercept points. Okay, there's 3 of them, and we'd have to find those individually. Finding out where this little hump happens. We're about to talk about that. A local maximum, the global maximum, figuring out where that happens. That's also a lot of work algebraically. But luckily we have technology right now. So 232, negative 1, 5. So this goes 232 and then negative 1, comma 5 for this one. Okay, so the domain and range. The domain is going to be all real numbers from negative infinity to positive infinity. And the range is going to be all numbers starting from negative infinity all the way up to the maximum value that it could be, which is at 32. So it starts at negative infinity and up through 32, inclusive of 32. Right, 32 is a potential value. I want to label this as the y and x-axis. Right, looks like that. Okay, how do we find that in our calculator? How do we type that into our calculator? Let's do that real quick. So let's clear this, go back to y equals, let's clear that equation, go back there, clear that equation, go up here. Okay, so we need to type in this really ugly equation. So I like to wrap it in parentheses because some of the older calculators have really ugly user interfaces here. So raising all those powers can get kind of ugly. So 12x to the power of 2, close parentheses. Oops, see how that got ugly? Delete that. Close parentheses. Plus, open parentheses, 4x to the power of 3, screw over, close parentheses, minus, parentheses, 3x to the power of 4, close parentheses. Okay, so there is my equation, and then the window, right? So if I didn't know where this was going, okay, by default, I like to do negative 20 to 20, and then reassess from there, depending on what the graph looks like at that point. Just the standard window of negative 20 to 20 graph. And I can see that I get most of my picture, but I'm missing part of it, so I know I'm going to have to let my y maximum go higher. I also can tell that I don't need to go all the way out to negative 20 and positive 20. It looks like very small values along the x-axis are good. And same thing for y. So the only one that needs to be big is the y maximum. Going back to my window, let's change this from negative 4 to positive 4. And negative, I don't know, 2 to positive 50 graph. Okay, so now it looks a little better. Looks like that. Okay, now I want to find this thing, right? From my graph, I could tell, you know what, I'm uncomfortable with this being so little. So let's just change my y minimum to be a little bit bigger. How about negative 10? Good. Okay, so now from my picture, I can tell that this is what I'm interested in, just this guy up here, for the purposes of finding the range, right? I can tell that I don't necessarily need that one for the range. It might be useful for other reasons, but not for the purpose of finding the range. That's the maximum value there. So how do we find that maximum value? So we're going to use this calculate button again. Second, calculate. And you see how it says maximum? We want to go down to where it says maximum. Maximum, hit enter. And now follow the instructions. It says left bound, and then it's going to say right bound. So you want to travel with your arrows here along the curvature, and you want to stay close to where you want to find the maximum value, somewhat close, but to the left of it. So say there, I'm going to hit enter, and it creates that little left bound. And now you want to go over the hump to the other side, somewhere on the other side, say over there, and then do the right bound. Hit enter. So what you've done is you've created or you've identified a little section of the domain in that little zone. And so now you hit guess. So go back to pretty close to where you think the max is. Hit enter, and now it finds the exact answer, 2,32. Good. So from that, we're able to come up with our rough sketch and be able to tell that this is 2,32. That this is 2,32 as an ordered pair. And now I can tell that every value from here below will be the range. As this travels over here, and you get to 32. then everywhere down here, going down toward negative infinity, all of these values will represent the range. No? Good? Okay, local maximums and minimums. So again, from the graph, it's really easy to identify what the maximum point, what the minimum points are. So we will be working with graphs and being able to spot them from the graphs. Later on, we'll build into cases where we have an equation and we have to find it from the equation. And these are really useful because there's a lot of places, a lot of applications where we want to find the maximum or we want to find the minimum. If we can come up with an equation that models a real-world situation, such as interest rates or production costs or just any number of real-world situations where an equation describes it. I don't know, speed of air around the wing of an airplane, the weight of a rocket as it's shooting up into outer space. It's obviously starts off really heavy because of the fuel, and as it's burning through the fuel, it becomes lighter and lighter and lighter. So there's some equations that can describe that. So we want maximum, maximum thrust as a function of the weight of the rocket, stuff like that. So we want the maximum, the minimums all the time. So again, if we just have a nice pretty picture, a nice graph, we can easily tell what all the local maximums are, right? It's a little hump, right? It's the king of the hill in a little section of the domain where the function is the maximum value. A little section of the domain where that little value there is the minimum value, right? That's what local maximums are. As you can see, you can have several of them, several local maximums, several local minimums. And then we'll define something called a global maximum, where global just means over the entire graph, which one is the absolute biggest one, whereas this is just the biggest one in a little section of the domain. Good? So the function value f of a is called a local max of f if it's true that f of x is greater than, f of a is greater than f of x when x is near a, right? So looking at this picture here, what we're pointing out is that this, come on, cooperate with me. We're almost done. Thank you. Okay, so we're saying that we would, we'd say that this value there, x equals to a, we would say that x equals to a, then that maps out to f of a. F of a is called a local maximum if it's true that there exists a little neighborhood around the value a, a little subsegment of the domain here, such that whenever you pick any x value in this little neighborhood, any other x value in here, and you evaluate it, in that little section, right, this leads to this. Here's f of x. For any other x value in this little green zone, not including the a, of course, it's always true that f of a is bigger than f of x, right? That's what this is saying. F of a is greater than or equal to f of x whenever x is near a, and that's what defines a local maximum. And then similarly, a local minimum. So let's say that this guy over here, I'm just going to use a different letter. Oh, that's fine, use a. So let's say that this guy is the a over here. This is a. We would say that this maps to some value over here, which is f of a, and it is considered a local minimum because if we think about a tiny little neighborhood around a, then whenever we pick any value of x in that little neighborhood, whenever x is chosen to a value close to there, it's always true that f of x is bigger than f of a. Therefore, we consider f of a to be a local minimum of that value. Okay, so again, don't let these definitions scare you too much right now. At this point, we're really just focusing on finding answers from a graph. So I think that that's pretty intuitive to find. And we'll also be using calculators a lot, or technology, Desmos, to find them. So graph them, and you can easily spot where the local maximums and minimums are. Good. Okay, so again, graphically, we take our equation, we graph it, and we can see that that point right there would be a local maximum at f of a, and that this point right here would be a local minimum at f of b. Notice that f of a is greater for all x close to a. Similarly, if there's a union rectangle. Okay, so that's just a matter of putting it on our calculator. So find this, round it to 3 decimal places. Okay, well, I think that this is the same skill that we just did a little bit ago. So we just covered how to find maximums a minute ago. It's the same thing for minimums. So I think you can take care of this. Yeah. Okay, that brings us to the end of this section.